Hello guys and gals, and welcome to this video on 5.6, which is about reaction energy profiles. So we will probably get through A and B, if not a little bit of C in this video, okay? So reaction energy profiles are a graph, really. So 5.6a says elementary reactions typically involve the breaking of some bonds and forming new ones. Okay, well, this is another topic that needs little to no discussion because we've already discussed it. Collision theory only applies to elementary reactions. Because complex reactions are made up of elementary reactions, it technically applies to them too. But if we're talking about just specifically what collision theory is discussing, it's elementary reactions. So because collision theory only applies to elementary reactions, then our definition of a chemical reaction, that bonds must be broken and or formed in order to have a chemical reaction, also only applies to elementary reactions, okay? So obviously, in a complex reaction, we are breaking and making bonds. But we are breaking and making bonds in the several elementary reactions that make up a complex reaction, okay? 5.6b says the reaction coordinate is the axis along which a complex set of motions is involved in rearranging reactants to form products can be plotted. Basically, this is a really fancy way of saying we can make a graph that shows the change in the energy as the reaction occurs, and that is called an energy profile. So, energy profiles with only one activation energy shown are for elementary reactions only, okay? So, this is an example of a reaction energy profile. And so as we can see here, the y-axis is energy. That's going to be potential energy, not the energy of the movement that's happening, right? Not kinetic energy, not the energy needed when they collide, but rather the potential energy stored in the bonds of the reactants and the products. The top here where it says transition state, that is actually that was what we'll talk about in 5.6c. The difference between that topmost point of energy and the reactant's starting potential energy, that is the activation energy. That is the energy that the reactants must have when they collide in order to overcome that and go on to make the products. And of course, we can see here the products have a lower form of energy. In this case, that will not always be the case. The x-axis is the progress of the reaction, which just means as you move from left to right, you're looking at the beginning of the reaction to the end of the reaction. Here's another example that we can look at. In this case, it's for an actual decomposition reaction in which bromine nitrogen monoxide is decomposing. And so at the top, again, we see that transition state, which we'll talk about in just a second, but the difference between that energy at the top and the reactant's potential energy, that is your activation energy. And then we go down again to the potential energy in the products. Okay, so 5.6c says the energy profile gives the energy along the reaction coordinate, which we just talked about. It says the reaction proceeds through the reactants to the transition state and to the products. The energy difference between the reactants and the transition state is the activation energy. So this section really has only two new things to add to 5.6b, and the first one is that idea of something called a transition state. So a transition state is the state corresponding to the highest point of energy in the graph. It is the least stable state in the reaction, and it only occurs for a brief moment at the moment of activation energy is met, okay? The specific form of the transition state depends on the mechanisms of a particular reaction. So transition state does not look the same for every reaction. It's important to note that transition state is not the same thing as an intermediate compound. Okay? An intermediate compound is formed in a complex reaction, and it is an actual compound. Now, it's still unstable, but it actually exists long enough to be involved in the reaction. The transition state is basically what occurs in the middle of a collision. It is not a compound, and it is not stable enough to continue to be involved in the reaction. So if we go back up here and we look at this, our transition state is actually a bond between the two bromine nitrogen monoxide compounds that would not normally exist. So basically, this is the point where those two bromine nitrogen monoxide molecules collide, and they actually form a brief bond with each other before breaking those bonds and going on to produce the products that we see from this reaction. Okay, so again, the transition state is going to look different for everything. It only lasts for a few minutes. It's not, or moments. It's not stable at all, and it cannot be involved in the reaction. The second idea that we're discussing here is this idea that bonds have potential energy stored in them. Okay, so a bond is not just an attraction of the electrons to two nuclei, or in the case of ionic, it's not just the attraction of two oppositely charged ions. It's actually a point where potential energy is held. It takes energy to form bonds. In order to force those electrons to be that close together, or in order to force those ions to be that close together, it actually takes energy to do that. But when a bond is broken, that energy is released. So there's so much energy stored in that bond, and then when we break it, that energy is released. The less potential energy stored in the bonds of a compound, the more stable that compound is. Okay? So the less potential energy that you have just hanging out in the bond, waiting to be released, the more stable the compound is. Again, the difference in the potential energy of the reactants and the energy of the transition state is actually the activation energy. Sometimes we can get confused, and we want to say this top piece here, where the transition state is what the activation energy is, but that's not true. It's actually the difference between that transition state energy and the energy held in the reactants. Okay? So, otherwise, this section is really just making sure we understand the pieces of those reaction energy profiles. The x-axis is the progress, the y-axis is potential energy. We always start with potential energy of the reactants, and as the reaction progresses, that energy is going to move through the transition state and finally end at the potential energy of the products. Now, it's important to note here that the potential energy of the products can be higher or lower than that of the reactants. And when that happens, it's going to give us a different kind of reaction. So if the potential energy of the products is lower than the reactants, we have what we call an exothermic reaction, meaning that heat is released. You guys have felt this before when we put calcium chloride into the water in Honors Chem. The water gets hotter as the reaction occurs. That's because when the bonds in the reactants break, a ton of energy is released. To form the bonds of the products, we only need to take a little bit of that energy. And so some of the energy that's released is used up to form the products, but then all that extra energy is left over, and it has to go somewhere. And so that extra energy is released to the surroundings, and it makes the beaker feel like it's getting hotter, because it is. It's increasing the energy of the water in the beaker. When the potential energy of the products is higher than that of the reactants, we have what we call an endothermic reaction, meaning that heat is absorbed into this reaction. You may have felt this when we put potassium chloride into water. The beaker gets colder as the reaction occurs, and this is because the reactants, when their bonds get broken and they release energy, it's not enough to form the products. And so what the reaction has to do is it starts to steal energy from its surroundings, making them colder and getting enough energy to form the products. So that is 5.6 A, B, and C. I hope that this made sense. Let me know if you have any questions.